Thanks so much, everybody, for bearing with me for these technical difficulties. So my name is Aly Sivji. You can find me on Twitter. I am at Sivjis. I'm one of the organizers of the Chicago Python users group. We call ourselves Chippy. I normally invite folks to come out to Chicago and come to a Chippy event if they ever happen to be in town on a Thursday night, but we've had to cancel all of our in-person meetups until it's safe to meet in large groups. But we have started live streaming our events to our YouTube channel. So if you go to our channel, hit the subscribe button, hit that bell icon, you'll get notified of our upcoming events. We actually have one tomorrow, so hope to see you all on the live stream. But before I do start, I do want to give a shout out to Grace, Daniel, and all the other members of the SF Python organizers. In Chicago for COVID, we had to cancel all of our events in March, and then we came back in April. And a lot of the things that we took, we learned from the experiences that these folks had in putting on an event. They wrote a blog post, and we used a lot of those learnings. So I just really want to say thank you. I took this talk out of retirement, submitted a proposal, sort of my way of saying thank you. All right, so let's get started. I normally don't like doing agenda slides, but I sort of have one here. We're going to start off by talking about data science for some context. We're going to learn about Docker. Then we're going to learn about containers. And then finally, we're going to talk about how we can use Docker for some data science workflows. So what is data science? Data science is about extracting value from data. It's about turning your data into actionable insights. And this can mean many different things. We could be visually exploring our data. We can build predictive models. We can classify observations into groups based on similar characteristics, or we can build data-driven applications. So first and foremost, I want us to all know that data science is a science. We have a question that we want to answer. We have a hypothesis of why something is happening. And our output, it's not just our findings, it's also the steps we took to get to our solution. And what this really means is that reproducibility, it's really important, and our analysis, it needs to be repeatable. So reproducible workflows in data science make it easier to communicate results. We can use our methodology to tell a story when we go and present our findings. If we have reproducible workflows, it makes it easy to defend decision-making. Instead of generating this, instead of using gut instinct, when we generate the same conclusions over and over again, we're making decisions based on data-driven insights. And finally, if we have reproducibility, other people can go in and audit our work to ensure that it's correct and that it complies with regulation. At one of my previous jobs, I used to work with healthcare data, and one of the things we needed to do was make sure that patient data didn't leak in any of our models. So this is a really good overview of the data science process. We start by asking an interesting question like, what are we trying to do? Next, we start gathering data to answer this question. And in this step, we're going to maybe transform data from a format we're storing it in into a format that's actually used for analysis. Next, we're going to do some exploratory data analysis. When we get to the machine learning phase, we're going to build the model. We're going to fit the model. And then finally, we're going to tune that model. And then when we have our results, we have to communicate them via a blog post, a paper, or maybe a presentation. So Python has a really great ecosystem of data science tools that enable us to do analysis. And Jupyter is sort of the star of the show. It's our data science front end that allows us to capture our process. So Jupyter notebooks are documents that contain live code, equations, visualizations, and explanatory text. Here's a picture I pulled from the Project Jupyter website. You can see we have some text, we have some formulas, we have some interactive sliders, some code blocks, and some visual output. And we can use all of these building blocks as components when we go and define our data science methodology. And we can also pass these notebooks around when we want to share results with colleagues. But not so fast. Jupyter notebooks suffer from one problem. That's the it works on my machine problem. In order for our notebooks to work, everybody's going to need to have access to the data, the code, as well as all the dependencies that were used to produce that initial calculation. And this is where Docker is going to come in. Docker is going to help us solve that problem of it works on my machine. So Docker is a platform that allows us to package and run applications in loosely isolated environments that we call containers. We can use the shipping container analogy to understand how Docker works. Shipping containers, they standardized the logistics industry. It didn't really matter what was inside these containers. We can send them by boat, by train, or by truck. And we have the infrastructure at all these various facilities to handle these standardized containers. With Docker, we can package up our code plus everything we need to run the code into an isolated container. And since these software containers are standardized, we can ship them off into different environments without having to worry if they're going to run or not. And if this sort of does sound similar to the concept of virtual machines, but there are a couple of key differences. The first is that containers, they run natively on the host machine's VM. That is, they share the same kernel as the host machine. And for virtual machines, we have a hypervisor. And this hypervisor, it provides each VM with virtual access to the host's resources. So what this means is with containers, we don't need full-scale operating systems. So they're going to be a lot more lightweight and have better performance characteristics. We can use Docker for many different types of things, such as streamlining our development workflows. If we want to do some continuous integration, some continuous deployment, we saw some great examples earlier. We can use Docker to build out microservices. And of course, we can use Docker to do some reproducible data science. This is a really good overview of the Docker architecture. On the left, we have the Docker client, and that's where we enter in commands to interact with Docker. These commands, they go to the Docker host, and this host could be your local machine, or it could be a remote machine. The host needs to be running the Docker daemon. This Docker daemon is going to listen to commands from our client. It's going to manage Docker objects like containers, like images, and it's also going to communicate with other Docker daemons. And then we have the registry, and that's where we store Docker images. Docker Hub, that's like GitHub. It's the public registry. So there you're going to find a lot of public images for things like Linux distributions, databases, and Python has a bunch of images up there as well. So each image is a frozen snapshot of a container. When we have an image, it consists of a set of read-only layers that are stacked on top of each other. And each layer is the set of differences from the layer below it. Containers are the runtime instance. When we create a container, what we do is we add a thin read-write layer called a container layer to the top of our image layer stack. And then anytime we make changes to our running container, so if we're creating a new file, modifying an existing file, or deleting a file, all of those changes are going to be done to that top read-write layer, that top container layer. This is really similar to the principles of object-oriented programming. Images are like classes, layers are akin to inheritance, and containers, they're runtime instances, just like objects are runtime instances of a class. We can create Docker images two different ways. The first way is to freeze our container using the Docker commit command. And what that's going to do, it's going to take that top read-write layer, that top container layer, and make it read-only. And then we can use this new image to initialize new containers. But the more preferred way is to use a Docker file and the Docker build command. So a Docker file, that's a file that contains commands that are used to create an image. And the Docker build command, that automates our build process. This is a list of common Docker file commands. So you have from that allows us to set the base image, like what image are we building off of? And here you're just going to use a repo name that you find on Docker Hub. We have label that allows us to set metadata. We can copy files and directories into our image. We can also set the environment variable and the working directory. The run command, it executes shell commands and it puts those commands in a new layer, and it puts that layer at the top of the image layer stack. And just be aware that anytime you use any Docker file command, we're going to be creating a new layer. So if we do say a run pip install Jupyter, next line we do a run pip install pandas, that's going to have two different layers. And one of the things that Docker best practices says is that we want to reduce the number of layers inside of our images. And so we can do that by chaining together commands like we would at the command line. So if we do a run pip install Jupyter, ampersand to chain them together, backslash to go on the next line, pip install pandas, we're only going to have one layer in that image. We can use entry point and CMD to define what our containers should do at runtime, like what shell command should be executed when our container launches. There's two ways we can put this in. There's the shell form, which is sort of what you would use at the terminal. And then there's the exec form. It's the same thing. It's formatted just a little bit differently. CMD and entry point do interact really well, but it's a little bit more of an advanced concept. So if you're just starting off with Docker, I recommend sticking with CMD. So this is our hello world Docker file. And let's actually go into the terminal and play around with this. So we have two files here. We have a hello world.py and a Docker file. So taking a look at that hello world.py file, I'm just going to be printing hello world. And taking a look at that Docker file, recall that every time we have a Docker file command, we're going to be creating a new layer. So we're going to use Python 383 as our base image. We're going to set our working directory to copy the contents of our current directory, which is this Docker file and the hello world py file, into that working directory. And then when the container launches, we're going to run Python on the hello world script. Did I just create this image? Yeah, I created this image. So let me just actually delete this image. So Docker RMI, hello world. Where's it? Okay, cool. And so I can build an image using the Docker build command. So I can do a Docker build. I want to tag this image as hello world. And I'm going to say the Docker file is in the current directory. That's where the dot comes in. And there it goes. It goes out, has those 4 steps, and it builds our image. So we can see all of our images using the Docker images command. And so you see here, we built hello world. It has a tag latest image ID, and we built it 9 seconds ago. And now we can use this image name to start up a container. So I could do a Docker run, paste my image name. It's going to go into that container and run Python and print hello world. We can also use the image ID to do exactly the same thing. So just do a Docker run with our image ID, which is just that hash you see, and it goes out, does the same thing. Now, if we want to see all of our running containers, we can use the Docker PS command, but we're not going to see anything here since our process did stop. So if we want to see all containers with stopped processes, we can use the -a flag. So you see here, we built a container. Let me make this a little bit easier to read. So we built a container off the hello world image. It has a command. We built it 28 seconds ago, and it also has a name, Lucid Loveless. So we can use this name to restart this container again. So I can do a Docker start -i and -a to connect standard in, standard out, and standard error. We're going to paste in our container name. And there it goes. It goes back and let me just do that again. It goes out and it prints that hello world. Pretty straightforward, right? So these are just sort of the commands I walk through. The commands just create a container and then restart that container. So you saw me use the Docker run command, and that's the command that you're going to use the most. And so let's explore this command in a little bit more detail. We can use the -d flag to run it in detach mode. As we saw, we can connect standard in, standard out, and standard error. We can also make our process run in a pseudo terminal. And if we want to set our name, we can use the double dash name. If we ever want to pass in parameters or maybe get into the shell of our container, we can pass in bin/sh or bin bash after the Docker run command to go to that respective prompt. So just be aware that anytime we delete a container, we delete all the data inside that container. So everything that was in that top read-write layer, that top container layer, it all just goes away. So we just need to think about different ways we can manage data inside of our containers. So the easiest way we can do it is we can use the docker cp command to copy files in and out of our containers. But you can already imagine that's going to get a little bit tedious. So the more preferred way is to mount a data volume. So what we're going to do is we're going to create a local folder and mount that local folder as a volume inside of our container. And then anytime we're making changes inside of that volume, it's going to be showing up in our local folder since we just mounted it there. So when we're creating a container with a Docker run command, we can use the -v flag to specify the host path we want to mount, and then the container path we want to mount to. We can also add a volume command to our Docker file, and this specifies where there could be a mount point. Just be aware that this doesn't do anything, and it's not really necessary. We still have to specify our mount with the -v flag, but this kind of description just helps us be more explicit about our build process. So when we're running processes in containers, we can connect to the outside world fairly easily, but we'll have to set up port forwarding to connect to the process inside of that container. This time when we're creating a container with the Docker run command, we'll use the -p flag to specify the host port we wish to forward, and then the container port we wish to expose. And just like with the mounts, we can use an expose command for the Docker file. This specifies that we might have a port forward here, but it doesn't do anything, but it's also just good to be explicit. Some Dockerfile best practices. I'm going to just stress this one more time. Be explicit about your build process. It's a lot easier to know what you did 2-3 months later if you have that explicit workflow in front of you. When we create a container, it shouldn't have any state. Try to use the Docker ignore file to prevent yourself from copying files you don't want inside of your images. When we're installing packages, make sure you only install the things you need, and afterwards you have to clean up your cache. Each container, it should only have one specific concern or purpose. I mentioned this before. We want to minimize the number of layers inside of our images. And I'm just going to mention the last one. I don't see this as much anymore. Maintainer used to be a Dockerfile command, but that's been deprecated. So if you can, use label going forward. So let's just review that container lifecycle process one more time, just to make sure everything is sticky in our head. We'll have a Docker file, and we can use the Docker build command to create an image. From that image, we can use the Docker run command to create a container. We didn't talk about kill, but if we do Docker kill container name, that's going to send a sigkill to the process inside of your container. We talked about starting a stop container. If we want to delete a container, we can do Docker rm container name. If we want to delete an image, we can do Docker rmi image name. This is a list of common Docker image commands I found. I put stars next to the ones I use more than others. Here's the same thing, except it's for containers. Some more tips and tricks. Smaller images are better. Only install the things you need. It might be worth exploring some other Linux distributions like Alpine Linux. Actually, like I wrote these slides like 2-3 years ago. I'm not sure if I would still give that same advice. Like every time I use Alpine Linux, I feel like I don't have some C dependencies and have to like go out and get them. So it's sort of just your mileage may vary. And I'm also just going to make a note of the last point. When we're setting an IP address for a process inside of the container, make sure you set it to 0.0.0.0. If we use 127.0.0.1, that's going to be a loopback interface, and we're not going to be able to connect to that process. Unfortunately, I did have to learn that the hard way. So the next section is going to be on how you can use Docker for some data science workflows. But before we do go there, I'm just going to check if there are any questions.
There is one question here. I'm seeing more about code as a service, which is one step down from containers. Any ideas here? Thank you, Paul.
Yeah, so code as a service. Let's actually talk about that a little later. So once we see what sort of Docker does, we can compare and contrast. Cool. I guess I'll just go on with the talk. Thanks for the questions. So I'm going to be just showing some templates of how you can use Docker for data science workflows. Nothing is really set in stone. These are just templates for you to use. Hopefully a place you can start when you have a project you can use this for. So imagine you have a Jupyter notebook you want to share. This could be a thesis, it could be a project deliverable, or it could be an analysis you want to send to a colleague. And we talked about this problem before, that Jupyter notebooks suffer from the it works on my machine problem. So the solution for this is what I call workflow number one, the self-contained container. What we're going to do is we're going to create a Docker image that contains all the libraries, the data, and the code required to produce our calculations. And then we're going to push that image up to Docker Hub. So here's that Docker file. We're going to go back into the terminal and play around with this example. So you see here, we have a Docker file, a data folder, and an iris analysis Jupyter notebook. So let's take a look at that Docker file. So I'm building off the Python 3.8.3 image, just updated today. I'm setting my metadata. I'm setting my working directory, copying the contents of my current directory into that working directory. So all the iris analysis and that data folder. I'm going to be pip installing some required libraries. So we got some NumPy, Pandas, Seaborn, sklearn, Jupyter, exposing my port, just being explicit about that. And then when the container launches, I'm going to run the Jupyter notebook command, set the port. And since we're in a container, we don't need a browser. And also, since I'm in a container and I'm root, I just need to turn that flag on to make sure things work. So I'm actually not going to go out and build this since it's going to take some time. But like a cooking show, I did do this a little earlier. So we have workflow number one, and I built this 4 hours ago. So we can take that image and use it to start up a new container. So we can do a Docker run. I want to connect my ports. I'm going to be 99.99 on my local machine, and I want to forward the Jupyter running instance of 88.88. And I'm just going to grab that image name. And there we go. We have this process running inside of a container. Oh, sorry, it's 99.99. Not? Oh, just give me 1 second. I have a notebook already up. That's what was going on. Okay. I was doing some demoing earlier, I think. Okay. Yeah. Now we should be good to go. I don't know what's going on. Let me try 0. Example was just working. There we go. So we have our process inside of this container. So let's just open up this notebook. And so we have just loading my imports. When I created this file, I had Python 361, and notice we have Python 383, just like we specified in that Docker file. And now I can load my data set. I can do some exploratory data analysis. I'm just rerunning these calculation cells. And at the bottom, I have scikit-learn SVM fitting. So let's just make sure that works as well. And there it goes. You can sort of see that classification using a very naive model. And all of these things work in a container, and we can just pass this around and not have to worry. So you're just walking through the steps. And now that we have our image, it's pretty easy to upload it to Docker Hub. We can do Docker login to log into our account, Docker push full image name to push that image to our Docker Hub. And then we can have instructions to Docker pull our image, and then instructions from the previous slide to initialize our container and then restart a container as required. So those of us that work on a team know how hard it is to standardize a development environment for everybody on that team. Or if you've ever accidentally updated a package and had everything break, you know how important it is to keep all your development environments isolated. And this is where Workflow 2 is going to come in. And I call this the data science project. And what we're going to do is we're going to create a team or a project image that contains a development environment. And then we're going to mount a data volume so we can have persistent data inside of our container. So some of the benefits of this are it allows us to separate our projects. If we want a startup, if we want to onboard a new employee, they can just start up a new container. And this kind of workflow also makes it easy to upgrade dependencies. If we ever have to upgrade one of our libraries to a new version, say Pandas releases a new version, we can run our automated tested pipeline on that new image with just that one version changed. We're all testing, right? And so this is the Docker file for the second workflow. Let's go back into the terminal, and we're going to play around with this example. And so here I just have a Docker file. So we're going to be building off the mini Conda image, and mini Conda is just Python with the Conda installer. Conda is super popular for data science, so I thought it'd be really fitting for this example. We're going to be setting our metadata, setting our working directory, copying the contents. Pip installing some dependencies. We got Jupyter, we got Pandas. We're going to clean up our cache. We're going to expose our port. And then we're going to create a mount point. We're going to be called /app. And then when the container launches, just like before, we're going to call Jupyter Notebook and set some parameters. I also pre-built this image a few hours ago. And so this time we can do a Docker run, connect our ports again. This time I'll make it 9999. We'll forward that Jupyter running instance of 8888. And now we're going to want to connect a volume. So here I have a volume where I sort of just do some of my data work. So just a folder on my computer. And then I want to mount this to /app. And notice this is why it's good to be explicit. I forgot from like 10 seconds ago. And then we can copy in our image name and hit enter to load up that process inside of that container. So now let's copy this URL. We'll go back to the browser. 9999. There we go. Okay, awesome. And you can see we have the same folder structure as that directory inside on my computer. So any changes I make when I'm in that container, they're all going to show up in this directory. So just walking through those steps I did to build the image, start up a container, then restart that container. Workflow number 3 is what I call the data-driven application, and this simplifies the deployment process. So we've all had to manually deploy an app. We run our tests in dev, then deploy to prod. We might have to run our tests in prod or run some sort of canaries in prod just to sort of make sure that things work. This doesn't really make a lot of sense. We want to pass things around without having to have that kind of worry. And so for this workflow, what I'm going to do is I'm going to package up a dashboard inside of a container. I'm going to have data on my local machine. And then every time I want to start up that process, I'm just going to start up that container if I want to view that dashboard. So let's just go back to that terminal. Flow 3. So here I have a Docker file, a plot time series file, and requirements.txt. So let's take a look at that requirements.txt. So these are all the things that I need to produce this dashboard. So I'm using Plotly's Dash framework. And now let's go and check out that Docker file. And so we're going to be building off the Python 383 image, setting our metadata, setting our working directory, copying the content of our current directory into that working directory, pip installing that requirements file, make sure we're deleting the cache, exposing the port, creating a mount point. And this time we're going to use entry point to define that Python is my default executable. And then we can use CMD to pass in default parameters. So here I'm going to pass in plot time series because I want to plot that one time series. If I had, say, another dashboard and another script, I can pass that file name in and run that separate dashboard if I so choose. So let's, I also pre-built this image using the Docker build command a few hours ago. And so let's create a container from this image. So we're going to connect our ports. Here I'm just going to have the same ports as what we expect. I'm going to mount a data volume. Let me just close that. And since like 20 minutes ago, I've been generating a number every 2 seconds between 1 and 5. And that's just in this folder right here. And I'm going to mount that to app/data. I'm going to copy in our image name. Actually, let's also give this one a name. So we'll just call this SF Python dashboard. And then paste in our container name, or sorry, image name. And then we have this process running. So you can see that our dashboard is updating with live data to that 2-second event delay that we were talking about. And I actually do have another script on my computer that's going to generate data just a little bit faster, every half a second, I believe. So you can see going back to our dashboard, the points are a lot closer together. So maybe instead of pointing on a file on your local computer, you can have a connection to a database, and then you can update your live dashboards, whatever delay you want to set your event timers to. Just walking through the steps to build an image, create a container, restart. So with workflow number 4, which I call the data science API, I want to make data scientists into data engineers. Data scientists are great at building models, but it's like, are they waiting for data engineers or machine learning engineers to go out and deploy them? So instead of actually waiting for somebody else to do it, why don't you just do it yourself? So with this workflow, what we're going to do is we're going to build and pickle a machine learning model. We're going to create an API around it that's going to take in predictions, produce an output, and then we're going to package up this pickled model with an API and deploy our image. We got yet another Docker file. So let's go back to that terminal. Close that. And here we have a Docker file, requirements file, and some IPython notebooks. So let's just take a look at that requirements file. And so here you see things like Flask, which I'm using to build my API, and sklearn and NumPy, which are things I'm using to build out my machine learning model. So I'm actually also going to show you, where is it? So this is the model that we're building. So just a very simple example. I'm loading in my data set, splitting it into my training set and my test set. I'm going to fit in a simple k-nearest neighbor on the iris data set. And then I'm just pickling that model. And here I have some code that's loading that pickled model, taking in an input point and producing a prediction. I take this code and I put it inside of my, my REST endpoint. And now let's go take a look at that Docker file. So here I'm building off the Python 365 Slim image. I tried to upgrade this to 383, but I was having some troubles. Just setting my metadata, setting my working directory, copying the contents of my current directory into the working directory. I'm sure folks here start seeing a pattern right now. Would it be pip installing my requirements file, exposing my port, and then we're going to be doing the entry point and CMD thing like we did before. I've also pre-built this image. So let's go out and create a container from this. Just give me one sec. I think I lost my... There we go. Okay, cool. Yeah, I just needed the command, sort of forgot that. It's minus P. Okay, so we can go... my terminals are all messed up right now. There we go. Okay, there we go. Okay, that's better. Okay, so we can go Docker run minus P 5,000, 5,000, and then we're going to have that image name. And yeah, we should be good to go. And so now my API is running on this endpoint, and I have, let me load this. I have some sample code that's going to load the request library, create a sample data point, hit my API, get a result back, and you can see that it predicted the number was 1. So I expected 1, I got 1. So you can sort of see it's not really about the answer with this talk. It's more about like connecting these dots so you can do predictions inside of a container. And here's sort of just those steps that I just worked through. So you saw me do a few different workflows. I just want to talk about a little bit about best practices. When we are creating Docker files, make sure to use the official Docker images. And here you can just find them on Docker Hub. Docker images do have versions. Make sure you're using them. Just don't only use latest. When we're using containers, we have to treat them as immutable objects. And what this means is that when you want to make a change to a container, you don't go in and make that change to the container. You go in, you change the Docker file, you use that Docker file to create a new image and use that image to create the container with the changes wanted. There's another really awesome workflow called multi-stage builds, and this helps you create your production images to be really small. And so what it's going to do, it's going to have intermediate build images that allow you to create artifacts, and then you can copy artifacts from these intermediate images to your final production image. And in my workflows, you saw me use root. That was sort of just the easy way forward. But when you're doing this in production, make sure you're running processes not as root. So now that we know about containers, we know about some new workflows, we have a different kind of abstraction we can blame. But seriously, we really shouldn't do this. If it works inside of a container, it's sort of your problem. You have to figure out why it's not working. That's pretty much it for me. What are some next steps? I have some links to the documentation if you want to install Docker. I really recommend their Getting Started guide. If you have a subscription to Pluralsight, Nigel Poulton has a course called Docker Deep Dive. CenturyLink has a fantastic Docker and Kubernetes resource. And myself and two of my co-organizers from Chicago Python, we put together a Docker for Data Science Python tutorial that's sort of based on this talk. It's this talk with a lot of workflow examples, so you can actually like get your hands dirty and get these concepts sort of drilled into your head. So that's it for me. Thanks so much for your time. Before I do go, I do want to give a shout out to the Chicago Python Users Group. I would not be where I am as a developer without that fantastic organizations. Also, I do have some upcoming speaking engagements. I'm going to be speaking at EuroPython, PyOhio, and PyCon Africa. Tickets are on sale. So thanks, everybody. Again, my name is Aly Sivji, and I'm open to taking your questions.